Krishna, whenever you're ready.
Okay. Good morning, everybody. Good afternoon to participants from the eastern side of the country. Welcome to the Graduate and Undergraduate Symposium organized by the Southern California section of the American Chemical Society. And we are grateful to the local section activities committee for granting an innovative projects grant, which made this symposium possible. And the focus of the grant proposal has been combating climate change through modern technology and combating diseases through advanced research with modern tools, including artificial intelligence. Our first speaker is Linnea Xu from UCLA, University of California at Los Angeles. She is an undergraduate student, and the title of her presentation is Characterizing Electrochemically Doped Semiconducting Polymers with varied anion sizes in different solvents. Linnea, go ahead, please.
Hi, I'll just share my screen really quick. Okay, hi, my name is Linnea, and this is my presentation on characterization of electrochemically doped semiconducting polymers with varied anion sizes. So semiconducting polymers are of interest to us because they make flexible and lightweight electronics like solar cells, as well as biocompatible electronics. And they're also more cost effective because they are processable in solution. So we're interested in improving and studying their conductivity so that they can be used for these applications. So here is the structure of our model semiconducting polymer, which is poly-3-hexylthiophene. It has this conjugated thiophene backbone with these hexyl side chains. And intrinsically, like most organic molecules, it has a pretty wide band gap, which means that there are pretty few charge carriers in the conduction band at room temperature. However, we can improve the conductivity by doping. And in the case of semiconducting polymers, we can introduce a molecule which has a lower energy LUMO than the HOMO of the polymer. And this is going to oxidize the polymer, resulting in the creation of charge carriers, which are evidenced by these new P1 and P2 transitions in the polaron case. When we remove one electron, this results in a polaron. And when we remove two electrons, this results in bipolarons, which actually decrease the conductivity because their mobility is poor. So we can do this with an oxidizing molecule, like in this case, or like what we're interested in is something that is more highly tunable, which is electrochemical doping. So I'll show you how we do that. So we can do that with the flooded cell, which is the diagram right here in the middle. And here we have the working electrode as our polymer, which has been spin coated on an indium tin oxide substrate. And there are two wires as the reference and counter electrodes. And then it's all in an organic solution of a lithium salt. So when we apply potential with a potentiostat to the cell, we can remove an electron from the P3HT film, put it into the ITO substrate, and then anion intercalation will happen into the P3HT substrate. So the polymer is semicrystalline and it has crystalline and amorphous regions, and we expect the crystal structure to change upon doping, which I'll talk a little bit about later. But in terms of the new energetic transitions, we're able to absorb these with UV-vis absorbance spectroscopy. So when we shine the light, the peaks correspond to the energy associated with these transitions here. And so we expect to see, upon doping, a lower absorbance at the intrinsic band gap here and higher absorbance at these lower energy transitions. So we expect that the size of the dopant anion is going to affect the mobility and creation of charge carriers because of Coulomb's law, that the force is inversely proportional to 1 over r squared, or is proportional to 1 over r squared. So we have these 3 different anions that we're interested in, and we expect that they're going to change the formation of charge carriers in P3HT, since there's no consensus quite yet on how the identity of the anion affects this formation of charge carriers. So to do this, we can take our cell and perform experiments such as cyclic voltammetry, where we are sweeping the current and measuring the resultant or sweeping the voltage and measuring the resultant current. And where we have peaks indicate the potentials at which we are oxidizing the polymer. So on the forward, our positive sweep, here we have the oxidation peak, and this is where we expect to see anion intercalation into the film. And then on the reduction peak, we expect to see deintercalation of anions or de-doping. So here is a sample CV that we took in air. And as you can see, after the first cycle, we get a lot of peak loss, which we don't see when we cycle under argon. So from this, we determined that we need to make our setup air-free. And in addition to making it air-free, we also want to be able to see the electronic structures that are happening as we're doping. So we have to make the setup both air-free and in the UV-Vis instrument. So I'll show you how we do this. Here is the UV-Vis cuvette with our 3 electrodes set up. We have the working electrode as the film here, and then the 2 counter and reference electrodes here. And then here's it actually in the UV-Vis instrument with the potentiostat attached. And so then here's a CV that we get in this setup. We get pretty good reversibility between the first and second cycle. And we see that the 4 peaks that we see in the first cycle are still there on the second cycle. So this is evidence that our air-free setup is working. And we know from previous studies that these first 2 peaks correspond to the crystalline and amorphous regions of the polymer, polaron formation in those regions respectively. And we're not super certain what's happening on these last 2 peaks. So we're particularly interested in what's happening at these high potentials, and especially how it changes depending on the anion. So here's what happens when we dope. I pre-cycled the film twice and then doped on the 3rd cycle, which is what you see on the right. And I've plotted the change in absorbance from the pristine polymer film. So we can see that if we dope right here before the onset of the first peak, we get no change in absorbance between the pristine and the doped film. But as we increase and dope, these colors correspond to doping at the first peak. And we start to see decrease in the intrinsic band gap and increase at these other P1, P2, and BP1 potentials. And then we can see the next peak, as well as the first bipolaron peak and the last bipolaron peak. And we see, especially at these high potentials that are happening at this last peak, that we start to see bleaching of the P2 peak. And this is associated with conversion from polarons to bipolarons. And this only happens at high potentials. So we can see kind of the same trends for each anion in the band gap bleaching and rising of the other 2 peaks, in addition to bleaching of the P2 peak at high potentials. So here are all of them with, this is perchlorate, and this is lithium. This is perchlorate, and this is sorry, bit of lag, but this is BF4. But we're interested in how all these 3 salts are comparing to each other when we dope. So if we're just looking at the band gap bleach, we can zoom in on this potential right here and plot the absorbances for each salt as a function of the doping level for each salt. So here's what we get when we do that. And we see that the smaller anions, which are the blue and green, are bleaching the band gap at lower potentials compared to our largest anion. And then we can also look at the bipolaron absorbance, which is this energy right here. And again, we can see that the smaller anions are creating bipolarons at lower potentials than our larger anion, which is in red, which is TFSI. So we hypothesize that this is due to the ability of TFSI to hold polarons at a greater distance from each other, thereby preventing them from coupling to form bipolarons. So additionally, we're interested in the effect of solvent swelling, because when we are electrochemically doping, the solvent has favorable interactions with the hexyl chains, and then this causes swelling. So the 3 solvents we're interested in are acetonitrile, ECDMC, and propylene carbonate. And acetonitrile is not swelling carbonate is moderately swelling, and propylene carbonate is our most swelling of the three. So all of our prior CVs were all in propylene carbonate, and we can see that after the first cycle, the second cycle, peak locations are shifting to the left, indicating that the solvent swelling is making it easier to intercalate anions on the second cycle. However, when we cycle with acetonitrile, we see that on this right plot here, that the subsequent curves after the first one are shifting to the right. And we hypothesize that this is due to regions are getting irreversibly doped. They're not fully dedoped on the negative sweep. And so then the next cycles are doping the remaining undoped regions, which is getting harder and harder with each subsequent cycle. And swelling would make it easier to intercalate anions, which is why we don't see it shift left, because this solvent doesn't swell. Additionally, I noticed when I did this that the P2 peak does not bleach as much as it did when doping with TFSI and propylene carbonate. So this led us to believe that swelling is having some effect on the conversion of polarons to bipolarons at high potentials. So in order to investigate this, this first one was done on the fourth cycle. And so I wanted to investigate and see if this would change if we doped on the first cycle when the film is not swollen at all. And in fact, it did change, and now the P2 peak begins to bleach at a much higher potential than when we were doping on the fourth cycle. So this is confirming our theory that swelling is having an effect on the conversion of polarons to bipolarons. Okay. So I also plotted the P2 peak versus the BP1 peak. And we can see that the more swelling the solvent is, here's red, which is propylene carbonate. The more swelling the solvent is, the more we see P2 diminish as BP1 gets to higher values. And it decreases, our P2 diminishes less, the more or the less swelling the solvent is. And then when we don't pre-cycle the film at all, we see very little P2 diminishing. And then if we look at the bipolaron absorbance as well, we see this entire curve is shifted to the right, or higher potentials, indicating that it's more resistant to forming bipolarons when it's not swollen. Okay, so I mentioned earlier about the crystal structure of P3HT, and we can observe that using this technique called grazing incidence wide angle X-ray diffraction, or GWAX. So here we're sending X-rays over the film, and at angles we have constructive interference, we get some intensity on the plot here. So P3HT is edge-on oriented, meaning that these peaks here are corresponding to the lamellar distance between the side chains. And this is actually where anions intercalate. So we are expecting that this distance is going to increase with the intercalation of anions. So we expect that upon ion insertion, we're going to get a greater lamellar distance, which is going to correspond to a lower Q value. So in order to look at the lamellar distance, we can integrate this region right here and at various radius values and get this plot on the right. And so Q is inversely proportional to D. So as the plots shift left, this is indicating an increase in the D spacing. So we can see that upon doping, all three of them are shifting to the left, so to greater distances than the intrinsic lamellar spacing of P3HT. And it's confirmed that TFSI is increasing the distance the most because it's the largest, followed by perchlorate, followed by BF4 in blue here. But this is all done at one doping level, and in our future directions, we want to get data for various salt and solvent pairs at different doping levels so that we can really see what's going on at each peak in the CV. So our conclusions from this work are that higher voltages are required to fully bleach the band gap and create bipolarons with TFSI. And we said that was probably because the TFSI is holding polarons at greater distances and preventing them from coupling. Additionally, bleaching of the P2 peak is happening at the lowest potential for the smaller anions. And we also saw that swelling seems to facilitate polaron to bipolaron conversion at these high potentials. So Thank you to my PI, Dr. Sarah Tolbert, and to my mentor, Nesabe, for all your support and guidance with this project. Are there any questions?
Hi, Linnea. Great presentation. I just had one quick question. How did you select solvents to determine the level of swelling for polaron to bipolaron conversion initially? Because I know you had listed like a few. Did you like do testing on like polar versus non-polar solvents, or how did you select the initial ones?
Yeah. So these three solvents, I'll go back to that slide. These three solvents were ones that we had previous data on from our collaborators, and we had swelling data on them as well. So I was interested in like looking at them because we had quantified the swelling previously. But I have also thought about the dielectric constant and how that is going to influence it, because these three also have various dielectric constants, but it seems that the trend is following this swelling effect rather than the dielectric constant. So I think that the swelling is having a greater impact here. But yeah, because we had quantified these before. Yeah, good question.
Great, thank you.
Linnea, you want to use this as a solid electrolyte in a battery setup, or what are the applications of this kind of polymers?
Yeah, so they can be used as like battery binder. So a lot of battery binders are like things that are insulating rather than conductive. And so to facilitate charge transport, we're interested in making these or replacing these with something that is semiconducting so that it doesn't impede charge transport as much.
Thank you very much. If there are no questions, further questions, thanks, Linnea, for a very good presentation.
Thank you.
Our next speaker is from UCLA. He's a graduate student, David Fay, and the title of his presentation is Examples of How Nanoscale Phase Separation in Solid Solution Electrodes Impacts Lithium-ion Battery Performance. Over to you, David.
All right, thank you. So yeah, my name is David, and today I want to tell you a little about a couple of my projects that involve putting in different transition metals into known electrode materials and seeing how that alters both the structural material properties as well as their performance as lithium-ion battery electrodes. And so zooming out for a second, we're probably all familiar with the importance of batteries in today's society, particularly in applications related to transitioning conventional energy grids to smart or renewable energy grids, as well as for the widespread adoption of electric vehicles. One important aspect of batteries that is actively being worked on right now is improving the charging speeds. So rather than having to wait 20 to 40 minutes to charge your EV, we would love it if you could do that on a time scale more comparable to filling up a combustion engine vehicle, just like at the gas station. And so looking at the requirements for fast charging or high power density, we can look at this Ragone plot here and see that batteries are positioned, looking at energy density here on the x-axis, as a energy storage device that has high energy density, so it can hold a lot per mass or per volume, but they're lacking in power density or how quickly they're able to deliver that energy. So like I said, there's active research in being able to push batteries up on this plot so they can deliver that high amount of energy in a quick amount of time. And so in order to do this, we have a couple key requirements for our material. There needs to be sufficient electrical conductivity. There needs to be high lithium ion mobility for lithium ions to move in our material. And then we need the absence or suppression of phase transitions, which I'll be talking about in the next slide, and are known to limit your charging or discharging ability in a battery. And so to make a little bit more sense of this, we can look at how lithium-ion batteries react. And so what I have here is just a basic chemical equation. So here we're looking at rutile-like molybdenum dioxide, which I'll be talking about for the rest of the talk. And so we start out as MO2 without any lithium present. Molybdenum is in the 4+ oxidation state through electrochemistry or applying current or voltage to our cell, we can reduce our molybdenum to molybdenum 3+, and part of that reduction reaction is incorporating lithium into the structure to make lithium MoO2. And so if we look at this at a structural level, we have exactly that, empty MoO2, where we insert lithium. But now talking about phase transitions, what happens is at a certain point, you could think of it as a solubility limit of lithium in this structure, right? We're adding in new elements to a crystal structure, so that creates strains. And so for most battery materials, you reach a point where your lithium concentration is too high and you can no longer incorporate additional lithium. And so in order to completely fill our structure and to continue charging or discharging, what needs to happen is what's known as a phase transition or a first order phase transition, in which we must nucleate and grow a new phase. So we're moving our atoms around in our crystal structure to be able to accommodate more lithium. And so this process is known to limit charging kinetics because, like I mentioned, you need to nucleate and grow this phase, which is known to be a slow process and often rate limiting. And we need to do that multiple times depending on the material in any given charge or discharge action, I guess. And so this also creates the issue of over time, when you have to do these phase transitions, you decrease the cycle life of your battery, meaning that the capacity that you're able to achieve when charging or discharging your battery decreases over time. And so this could be understood because we have a near instantaneous volume change of our material, which causes a lot of strain on the particle level. And so over many cycles, you can begin to crack or even destroy your particles. So that's why that's one of the main reasons why when you use a battery over and over again, you can't get as much energy out of it over time. And so mentioned we're studying molybdenum dioxide, which is a well-known lithium ion insertion material. It's been studied in our group at the Tolbert Lab at UCLA. And it's not a particularly good battery material in the sense that you probably would never want to make a car with it. But it is a very interesting system to study fundamental chemistry and crystal chemistry with regards to lithium insertion and removal. So in that way, we think of MoO2 as a model system. And so going back to our requirements for fast lithium ion charging and discharging, we can see that looking at the structure here, there are tunnels, which are one of the preferred motifs for lithium diffusion. So allowing lithium to travel through these tunnels and reach the molybdenum in a quick way to facilitate that lithiation reaction, that reduction reaction of our molybdenum. And then it also has good electrical conductivity. So two of our requirements for fast charging. What it does experience, however, is a series of phase transitions, which again, I mentioned can be rate limiting. And so by using this as a model system, we can alter the material both at the macro level. So there's been a lot of work done on nano-size MoO2 and how that affects the phase transitions, but we could also tune the composition chemically through substitution. And so in this table here, I've shown potential transition metals that you're able to substitute for molybdenum in the structure, and we'll see how that can affect the performance. And so just really quickly want to discuss how we make these materials. And we use a sol gel-based method in which we take various molybdenum and tungsten precursors, we dissolve them in a solvent to get nice solution-like mixing of our transition metals. And then we slowly dry it overnight. And the precursors we've chosen undergo a series of hydrolysis and condensation reactions, which eventually allow us to gel our material into a semi-crystalline gel precursor, which we can then put in a reducing atmosphere. And you can see that you can obtain the product at a variety of temperatures and heating conditions to yield these molybdenum tungsten solid solutions or mixed transition metal oxides that I'm showing an SEM micrograph of right now. And so these materials already, when you mix transition metals, and these are just select examples of a few of such solid solutions, we can see here in diamonds that our mixed molybdenum tungsten and mixed molybdenum niobium solutions far outperform the molybdenum, tungsten, and niobium equivalent structures on their own. What we're looking at here is a charged discharge plot where on the y-axis, we're measuring the capacity or how much lithium is able to be stored in our material. And each one of these points represents a charge and discharge cycle and how much of that lithium reaction they're able to participate in. And these different C values here describe the different charging speeds. So here at C/2, we're looking at a charge in 2 hours and a discharge in 2 hours. 1C is a charge in 1 hour, discharge in 1 hour. 2C is in half an hour, and so on. And so we can see, and this is true across battery materials, that as you charge your batteries faster, you're able to access less of that capacity. However, when we compare our battery materials, we can see that we're able to get a lot more of our capacity at different charging speeds compared to just the pure materials. And so this is just to show that the solid solutions do outperform their single element counterparts. And this could be understood because, well, we'll talk about phase transition mechanisms, but also it is widely known that if you incorporate the right element into your structure, this can increase lithium ion diffusion, which again is a critical requirement for fast charging in batteries. But even within the same solid solution, so if we have notionally the same solid solution, so we put in the same materials, we make them under very similar conditions. They have they index to the same crystal structure as I'm showing with these powder X-ray diffraction patterns. They have roughly the same secondary particle size, which are known in the battery literature to affect charging and discharging speed. If we look at a metric like how much charge you can get in 6 minutes, so a very fast charging speed, we can see that two samples that are notionally identical can get upwards of 6 times the capacity in samples that should be, at least from bulk analysis, very similar. And so the reason for this, we've discovered, is that even though you're able to index a certain material to a certain phase, at a nanoscale, there might be a level of separation. So what I'm showing in a cartoon here is this purple would represent a well-mixed solid solution of molybdenum and tungsten, where at each crystal site, you have an equal probability of having molybdenum or tungsten, or each lattice site that is, versus a case where we have, although particle on its own through bulk methods might look like a solid solution of molybdenum and tungsten, we actually have domains, small nano domains of pure molybdenum or molybdenum enriched domains, as well as tungsten enriched domains. And so we understand now that by despite being able to achieve this phase at various conditions, there are certain synthesis kinetic considerations that allow you to have more mixed or more separated solid solutions. And so just going ahead here and how we can infer that, we have some methods such as pair distribution function analysis and XFs that support this, but here's a more visual way to look at that, talking about CV. So like Linnea mentioned in the last presentation, cyclic voltammetry, where we take an electrochemical system and we alter the voltage at a set rate, gives insight into redox reactions. So what I have plotted here in red is the CV of molybdenum dioxide, and in blue is of tungsten dioxide. And each of these peaks correspond to molybdenum 4+ and 3+, each of these sets of peaks, redox reactions, and the same for tungsten. And so what we could expect when we mix these two materials into a solid solution is if we have a nano-separated material, we'll see something that looks more like a combination of the two with well-defined peaks spread across this whole voltage range that we see. And indeed, that is what we see when we make a separated solid solution, again, using some of those turning the knobs in our synthesis. We can see that we have well-defined peaks that are shifted inward, which is indicative of transition metal mixing. However, we can see that they are close to their single element counterparts, versus when we make a more mixed solid solution, we can see that the redox reactions are in a more concentrated voltage range, and that there are less clearly defined peaks, which again would indicate that rather than having small domains that are enriched with molybdenum or enriched with tungsten, we've achieved better mixing where there is a random distribution of each element. Okay, and so just to, again, visualize that we're operating on a spectrum here where even though, so represented by this purple outline here, we can look at something through XRD and say that something is 1 molybdenum, 1 tungsten dioxide. What we can instead have is at the nanoscale, there's a wide range of local mixings that can happen. And we'll see right now that that has an effect on phase transition behavior. And so just to show a little more battery cycling here, the main takeaway from here is saying, okay, we have these solid solutions that are made in an identical way, except the only thing we're changing is the temperature that we synthesize them at. And we can see a trend where we start at a low temperature and we crystallize our material where it peaks at 750 degrees. But past that point, so crystallinity is good for enhancing lithium ion diffusion kinetics, so faster charging and discharging. At a certain point, that higher temperature starts to encourage phase separation, and we see a drop in performance all the way down here to when we heat them up at 950 degrees, where they perform quite poorly at not just fast rates, but slow rates too. And again, this is just to demonstrate that notionally identical materials can have very different performances as electrode materials, depending on their local phase separation. And so investigating some of the mechanism of this a little bit more, we can use operando synchrotron diffraction. And so synchrotron diffraction, so using very strong X-rays, we can take our battery materials to a synchrotron such as the Stanford synchrotron radiation light source, where we are shooting these very strong X-rays through our battery as we operate it. And what we're looking at here in these heat plots, and so this is an example with just regular MOO2. This is a zoomed in XRD peak. We can see, so we're looking face down on it. We can watch as we discharge or charge our battery that our diffraction peaks shift. So we start at some 2 theta or Q value. So corresponds with a D spacing, right? So we move to a lower 2 theta, which, because we're in reciprocal space for X-ray diffraction, corresponds with an expansion of the unit cell. And this should make sense. We're putting lithium into our material, so we expand the structure. And then we reach this gap here for regular MO2. And that is what I was talking about earlier. When you reach a solubility limit of lithium, right, we can no longer accommodate lithium. So instead of continually expanding our material into a larger size, we see the nucleation and growth of a new phase here that is able to accept the more lithium. And then that continues to grow, and then it continues down. Just seeing stuff. The chat here. Okay, great. I'd be happy to answer that question in the end. That is definitely a good question about batteries. Okay, and so this is an example of just pure MO2. And so looking at some of our solid solutions, we can see that we've modulated the phase behavior. Oh, and then so this is just to show that, again, these phase transitions can be correlated with redox events in our cyclic voltammetry. Okay, and so looking at some of our more phase-separated solid solutions, just the takeaway from here is that we have increased the amount of phase transitions that are present. In fact, we can see a molybdenum-rich and a tungsten-rich phase reacting separately. And again, we don't want phase transitions. That's known to limit our material performance as well as to cause more degradation. And then in case where we have a more well-mixed material, we can see that there is a single phase reacting in a smooth, continuous manner. And so that in this case, we have suppressed the discontinuous phase transition, and that can be interpreted as allowing the material to expand at all of these spacings without the need to nucleate and grow a new structure. And in this case, that's aided by the larger tungsten atom making essentially pre-expanding your material so that it is more accommodating of lithium in the first place. Okay, and then so just really quickly to show examples of how this could impact cycle life, we already saw in the bar graph previously that the continuous phase mechanism where you don't have to nucleate and grow a new phase can lead to considerably faster fast charging or considerably better fast charging. And so an example here is that in red, we have a fairly separated solid solution. In green, we have a pretty well mixed solid solution. And in yellow, we have an intermediately mixed solid solution with our MO2 control here in pink. And just one thing to notice is, or a couple things to notice here, is that our separated solid solution crashes its capacity despite them all starting at around the same. Intermediate one loses a decent amount, and then the mixed solid solution, while starting at a lower overall capacity, has the highest capacity retention. So over 250 cycles, it's able to maintain more of its capacity compared to the other solid solutions. And then just to give another example, this time with molybdenum and niobium, same idea here. The exact details aren't important, but we can see that solid solutions that are separated, such as in blue and as pink here, have a large decline. Intermediate samples, such as in red, have a intermediate decline. And then this black sample here, which we believe is completely well mixed, while it does have a lower starting capacity, it maintains that very well across many cycles. And so hope that wasn't too rushed, but I hope I was able to communicate that you can modulate this phase behavior through substitutional disorder or putting in different transition metals into our structure, and that these phase transitions have a large effect on your performance as a lithium-ion battery. So your rate capability, how fast you're able to charge and discharge, how much capacity you get at those fast speeds, and then also your cycle life, how long your battery is able to last over many cycles. And that despite the fact that traditional bulk analysis techniques such as powder X-ray diffraction or scanning electron microscopy can show that materials are seemingly identical from a certain perspective, we can see through techniques such as cyclic voltammetry, which reveals local chemical reactivity, that there could be nanoscale separation of our materials that has a big impact on their performance as lithium-ion batteries. Okay, so with that, I would like to thank my advisor, Professor Sarah Tolbert, for giving me the opportunity to do research in her group. My mentors, Danny and Helen and Yi, my mentees, Ewing, who had a really large part in creating and characterizing a lot of these samples, Sarah and John, the National Science Foundation for sponsoring me. I would like to thank the organizers of the symposium for giving us the opportunity to share our research, and you for listening. Thank you very much. Be happy to answer questions now.
There are 3 questions in the chat. Can you see them?
We're already
Yeah.
about 10 minutes over into the next presentation.
So we'll go with one question perhaps.
Okay. Is the separation expected to increase over time without use? No, because when you're not using it, your structure is kind of remaining static, and you have a solid structure, so the transition metals won't be able to move around a lot. Like solid state diffusion is quite slow. Biggest challenges for gelling, honestly, I haven't looked too much into different gelling approaches. They're fairly well behaved, but in a lot of other systems, you can have issues with solubility or things crashing out, or if there is a really high tendency for materials to segregate out as you dry slowly, you might want to do something like freeze drying. Do you have a sense of the size of these crystals and the mean free path of the lithium ion? Mean free path, I don't have a good number on about the size of the crystals. So secondary particles are hundreds of nanometers, so maybe like 60 to 300 nanometers. And then diffusion distances, they're hopping from lattice site to lattice site, and that's on the order of several angstroms.
Thank you very much, David.
Thank you all for your attention.
Yeah. Our next speaker is Rebecca Tourier from SUNY Brooklyn College. She is an undergraduate, and she will be speaking about platinum 4 gold 1 compounds containing the carboplatin core as potential ovarian cancer chemotherapeutics. Over to Rebecca.
Thank you so much for the introduction. Yes, so I'll just share my screen and we can get right into it. Okay. How do I do this? All right. Hi there, everybody. My name is Rebecca Toure, and I'm an undergraduate at the City University of New York, Brooklyn College, where I study chemistry and I work in the lab of Maria Quintel. We synthesize transition metal-based complexes and evaluate their anti-cancer activities. I, in particular, work with platinum-4 and gold-1 heterometallic compounds, and I deal with ovarian cancer. So, to begin, platinum-2 drugs are the standard for cancer. One that's been around for a very long time is cisplatin. Cisplatin was first FDA approved in 1978, and it was FDA approved for testicular cancer, but it was shown to have efficacies against different types of cancers, like ovarian, colorectal, and triple negative breast cancer as well. Unfortunately, though, that drug suffers from cytotoxicity and nephrotoxicity issues. Platinum-2 drugs in particular follow the mechanism of binding to purine bases, adenine and guanine in DNA, and induce apoptosis by essentially breaking the double helix of the DNA. It's highly reactive, and it does a great job at breaking DNA when it gets to the nucleus, but unfortunately, it suffers from side reactions and leading to side effects and reduced bioavailability. To combat that, derivatives of cisplatin were created, carboplatin, which is now the choice drug against ovarian cancer, and oxaliplatin, which is now the choice drug against colorectal and testicular cancer. Unfortunately, though, these drugs still suffer from the same cytotoxicity and nephrotoxicity issues, though it's not to the same extent as cisplatin. To combat this, platinum-4 drugs were created, such that within cellular milieu, these platinum-4 drugs can undergo reducing to become platinum-2 drugs by reducing agents like ascorbic acid or glutathione. In this way, we can still have the power of the platinum-2 drug, and this increases bioavailability and reduces side reactions. So with that, I'm going to transition now to FDA-approved gold-1 drugs. So they follow a similar mechanism of action where they bind to DNA, but you will find it more in the mitochondria. This drug that I have listed
Hi,
here.
Rebecca. I just wanted to chime in really quick. I think you might be sharing the wrong PowerPoint screen. So we're still on slide 1.
Oh, you are?
Yes.
I think I might be frozen.
That's fine. Maybe if you unshare and then share again.
Okay, let me try that. Okay, let's see. Okay. Okay, can you see my gold compound here now?
Yes, we do. Thank you so much.
Lovely.
Okay.
Thank you so much. All right, continuing further. They follow a similar mechanism of action. However, you are more likely to find gold-based drugs in the mitochondria of cancer cells. Now, this one that's here pictured on the screen is Oranafin. And Oranafin was first approved for use against rheumatoid arthritis in 1985. Unfortunately, though, it still suffers from cytotoxicity and nephrotoxicity issues. But I mentioned that platinum-2 drugs work by attacking the nucleus, and gold drugs also work by attacking the nucleus, but have a better job with the mitochondria. We decided in our lab if we could take the best of both worlds and to create a heterometallic compound, combining these two different mechanisms of action, leading to now platinum-4 gold-1 compounds containing gold-1 fragments. And this is a previously published work that we've done in our lab where we created heterometallic compounds using a platinum-4 core along with gold-1 linkers, and we evaluated its efficacies against triple-negative breast cancer. We did it using a cisplatin core, which is PTAU3, another cisplatin core, but this is our binuclear, our trinuclear model for PTAU24. And then we used oxaliplatin core, again, our trinuclear, which paid PTAU25. Now, considering that, we saw that we had a variety of results. We saw the best results with our trinuclear model with the oxaliplatin core, where we have IC50 values of 5.87 in breast cancer, 2.99 in ovarian, and we found that it had the best selectivity index, meaning that there was a reduction of the unnecessary, unwanted side effects, side reactions causing these side effects. So because we saw good results with our PTAU2 compound, we decided, let's try it with the carboplatin core. So our main goal is to synthesize a platinum-4 gold-1 heterometallic compound using a carboplatin core. And then once we get that, we can evaluate its anti-cancer activity against the panel of ovarian cancer cells, including cisplatin-resistant kind, and ultimately to increase clinically available treatment options. So we first created the heterometallic compound. We have multiple methods for synthesizing, but our primary one is beginning with the gold-1 compound, where we used our platinum-4. We ran the reaction dry DMF at room temperature for 24 hours using coupling reagents TBTU and triethylamine to obtain our PTAU6. That's one method. But we also saw that we could synthesize it using an activated ester form of the gold-1 compound, along with the platinum-4 in DMSO for 16 hours at 60 degrees, and we can also obtain a platinum-4 gold-1 heterometallic compound. We got better results using the DMF and coupling reagents, so we continued further with that. Our structures were confirmed using HNMR, 195 platinum NMR, along with 31 phosphorus NMR. And this is for our heterometallic compound using a hydroxy and acetyl group in the axial positions. Because we had success synthesizing that, we decided using a dihydroxy core. So first we had to synthesize our platinum-4 compound. I did that in collaboration with my lab mate David, where we synthesized our platinum-4 compound using a procedure from the lab of Guangyu Zhao, and we successfully reproduced it. Now, with that, we aim to create our heterometallic compounds, again, using gold-1 linkers, where we have our binuclear model, that is PTAU7, and then we have our trinuclear model using which is PTAU28. I will say, though, we haven't yet reached this step, because unfortunately, our current synthetic methods are in need of optimization. Previously, our PTAU compounds had yields of around 30 to 40% of the pure product. Our PTAU6 synthesis had similar results. However, though, we suffered with being able to properly purify the final product. Our first step, just to get our crude product, was around 30 to 40% yield. And after purification, we had little to no product remaining. And unfortunately, to synthesize these compounds, the time cost is high. It took us around 5 days in order to yield just one product. But before we can, to improve in that way, I would like to, yes, decrease the time cost, but to celebrate, I would say that we have obtained a heterometallic compound using the acetylated platinum 4 carboplatin core. So further optimization is needed to look into the purification methods for this heterometallic compound synthesis. But once we can get that done, we'll evaluate its efficacy against different types of cancers, including ovarian cancer. We'd also like to synthesize binuclear and trinuclear models using cationic moieties like N-heterocyclic carbines and the 4-diphenyl benzoic acid linker. And I just want to say thank you so much to my PI, Maria Quintel, for telling me about this opportunity and for mentoring me through this whole process. I'd like to thank my lab mates, David in particular, for working with me on this project, and the biology team that evaluates its anti-cancer activities. I'd like to thank the NIH for funding me, the American Cancer Society for also funding me in my summer research, Brooklyn College and its Cancer Center, and you all, of course, for listening to me. Thank you very much for your time. I'll be glad to take any questions.
There are 2 questions in the chat. If you can see them, Rebecca. How did you
Yes, I
confirm
can.
that?
Lovely.
Okay.
Alrighty. First question. How did you confirm that you produced the trans versus cis
You're getting
PTAE
cut off.
compounds? So this is a great question. With trans or cis, hello? Okay, can you guys hear me?
Yeah.
Okay, lovely. So for the PTAU heterometallic compounds, we did not observe any sort of isomerization occurring between the cis or the trans isomers. We only saw that we got the cis, and that, how do you say? I guess it wasn't exactly something we were looking out for because we hadn't had issues doing that in the past. At least I would say for my current compounds that I'm synthesizing. For the next question, what are the ways you could speed up the synthesis in the future? Do you have an idea of the side reactions leading to only 40% purity? I'm actually not sure what we could do to speed up our synthesis, considering just to synthesize carboplatin alone, it takes around 20 hours minimum, and that's just the starting material. I think that all comes down to the, how do you say, it comes down to the ligands present within the molecule. When we had our synthesis for the cisplatin core, it was much shorter. It took around 3 days to obtain a product, and that was the fully purified product. I would like to get back to you with an answer for that question, but as for any of the side reactions, I would think it's possible. Maybe we do have isomerization occurring there, leading to only 40% purity, which eventually gets washed out after we filter. That's one of the ideas that I have. But I would like to look into that further. Thank you for your questions.
Thank you. Thank you, Rebecca. Thank you very much. Our next speaker is from the University of Southern California, Yashvi Tomar, a graduate student, and the title is Reliable Grid Energy Storage, Selenide Additives Improve Iron Electrode Performance and Longevity in Alkaline Batteries.
Hi,
Go ahead, Yashvi.
thank you. Hi everyone. So I will be talking about the rechargeable batteries, specifically how I found selenium and selenate-based additives improve the performance of iron electrodes. So to give you a context, iron-based batteries, they hold a great potential for large-scale energy storage devices. If you look at the statistics, the amount of electricity generated by resource type in the USA, it was 14% was coming from renewable sources. And the DOE, the Department of Energy, they wanted to increase it to 38% by 2050, and that is a huge increase. What does that mean for you and me? So basically, since renewable sources are variable in nature, that means that it makes the grid very unreliable. It leads to power outages and disturbances that currently cost industrial and digital firms collectively $52 billion annually. And this is a huge loss. And to compensate it, what what actually is out there is you use an energy storage devices. So when these renewable sources are in surplus, you store the energy and you can then use it at a later stage of time whenever the demand is high and the renewable sources is not available, which is quite great. And if you look at the different aqueous battery types here, it compares these batteries on the basis of cost, the life cycles, and you would see that the batteries that consist iron electrode like nickel iron or iron air, they comes as a more practical solution given their extremely low course. Their life cycle has a big upper hand. They can go cycle up to 2000 cycles. Their energy densities, their Coulombic efficiencies are quite moderate as well. So they hold a great potential. And going into the chemistry, so I would just want you to take a mental note of these reactions. It will be helpful when you're moving along with the presentation. So during the charge, the iron electrode, what happens is iron dihydroxide converts to iron, and the reverse of that reaction happens during the discharge. Very simple. And for my battery testing, what I do, this is the setup that I use. My working electrode would be iron, which is negative. The positive electrode would be nickel, and the reference would be MMO. The battery electrolyte would be 30% weight by volume potassium hydroxide. So moving on to the challenges with these electrodes that hinders their practical application, and one of them is the poor discharge rate capability. So David, I think already explained it, but I will just go over what discharge rate capability means. It basically tells you how efficient is your electrode or the battery in discharging at different rates. What happens with iron electrode specifically, when you discharge, iron converts to iron dihydroxide. And iron dihydroxide is insulating in nature, so it forms a layer onto the surface and completely passivates it. So no further electrochemical reactions can proceed, leading to very poor discharge efficiencies. So in literature, people found that just adding a small amount of iron sulfide, like 5% of the electrode weight, would greatly enhance this disadvantage. So what was this sulfide doing? It was providing the conductive matrix, and also the sulfide would react with this insulating iron dihydroxide to produce iron sulfide. However, there is a certain challenge with this additive, because of which we wanted to look for alternative additives, and I will explain you just now what is wrong with this additive. So with passage of time, these sulfide ion, they would dissolve and get oxidized onto the positive electrode to sulfate ions. And the problem is converting sulfate back to sulfide. The reduction of sulfate to sulfide is kinetically challenging. And this means that with passage of time, the electrode is losing the depassivating reserve of additive. And this greatly enhances, disadvantages in the terms of the life cycle of the electrode, where you have to every time add this additive so that you can again go back to the better discharging capacities. So we wanted to find an alternate additive so that we can enhance the life cycle of the electrode, and we don't have to every time go back to add this exhaustive depassivating agent. So selenium based additive comes out as an alternate solution, because selenium sits right below the sulfur on the periodic table, and it has similar chemical and physical properties, and was also found to be electrochemically reversible, as I will discuss about it in my coming slides. So moving right into the discussion of what I found with this selenium additive. So I will try to answer these three questions. First, let's look into how changing the iron sulfide in the additive to iron selenide impacts the iron electrode chemistry. And To make my cells, I start by mixing these 5 additives and grind them in a mortar pestle. 70% by weight of this is carbonyl iron, 5% by weight is the active additive, which is iron sulfide or iron selenide. Once I have this completely grinded, I place them on a nickel mesh, which act as a current collector, and hot press this assembly. So after hot pressing, I set up this 3 electrode cell, and now I'm good to go with testing these additives. So once this whole cell is set up, I do the formation of electrode, which is a very crucial step. Every electrode has to go through it. It simply means formation means it simply means that I'm activating my electrode until I get a stable discharge capacity. So in this chart, as you see, it shows how the specific capacity varies with respect to the cycle number. When iron sulfide or iron selenide is present, and as you can see, it takes around 50 to 60 cycles with both the additives to form the electrode completely, with the stable discharge capacities of around 0.23 to 0.25 ampere hour per gram, which is quite great. This tells us that this another additive, iron selenide, did not introduce any significant changes in terms of formation capacity. And the other parameter that we look into these iron electrode is the polarization curves. So polarization curve, basically you plot the potential with respect to the specific capacity, and it tells you exactly how each respective cycle the charge and discharge profiles look like. So during the formation for iron selenide, with each respective cycle, this voltage plateau keeps on increasing and becomes stable by the 40th and 50th cycle, which indicates the end of the formation. So coming to the comparison of both the additives after the end of formation, in terms of their polarization curves, you can see that the polarization curves are quite similar. The feature is quite similar. That indicates that this additive does not introduce any significant electrochemical changes into the electrode and can serve as a good alternate additive. And moving on, the other way I tried to introduce this additive was through the electrolyte. The motivation to do this study was because selenium is extremely low abundance and it's extremely toxic. So we wanted to minimize the usage of this additive to as minimum value as possible. So I made 2 cells for controlled study. So I introduced selenium salt and sulfate salts into the electrolyte itself, and then tested the batteries and see how it performs. So to our surprise, or what we already expected, but in the formation capacities, since sulfates cannot be kinetically converted back to sulfides, there is no depassivating agent, and during the formation, the discharge capacity sits at zero. Whereas when selenium is present into the battery electrolyte, the electrode starts on very slowly forming until a stable discharge capacity is attained, that is around 0.23 ampere hour per gram, very close to what we were seeing when the additive is present in the electrode itself. And even if we look at these polarization curve of these both electrodes, you will understand more clearly of what's happening. When sodium sulfate is present in the electrolyte, there is no voltage plateau during the charging, and this indicates that the electrode is completely passivated, and all of the charges going towards the parasitic hydrogen evolution reaction. And moving on, so now we introduced the additive through the electrode and the electrolyte. The next thing was to study their discharge rate capabilities. To do that, I charge the electrode at the constant rate of C/2 and then discharge at different rates of from C/5 to 1C rate. And as you can see, the capacity retention for iron sulfide is slightly higher compared to selenium-based additives. But I want you to take away from this slide that for selenium-based additives, whether present in electrode or in electrolyte, the capacity retention is well maintained, going from very low rates of C/5 discharge to very high rates of 1C, which tells that this additive can serve as a good depassivating agent and was able to attain a good discharge capacities at various discharge rates. So moving on. So moving on to the next section of the talk, which is how reversible is selenium under battery operating conditions. So if you look at the full battery scale, the positive electrode is nickel, and commercially you can also use an air electrode, and these electrodes sit at a potential of around 0.4 to 0.5 volt positive, and the negative iron electrode sits at around minus 1.2 volts. So I wanted to see how selenium would behave in that potential window, and for that we do the very simple electrochemical analysis, which is cyclic voltammetry. So from these cyclic voltammetry analysis of sodium selenide, I found that by the 30th cycle, as you can see, the CV becomes quite stable with well-defined oxidation and the reduction peaks. This indicates that the selenium is extremely reversible under the battery operating condition, which also adds up to our hypothesis of it being an electrochemically reversible. And moving on to the last section of the talk, which is to see how this additive enhances the life cycle of the electrode. And this will just very beautifully bring everything together, which we have already been through. So what I did was I did life cycle studies at C/2 rate. So C/2 rate means 2 hours of charge and discharge to maximum capacity. And when iron sulfide is present, the capacity retention with respect to the cycle number, as you can see, the capacity drops to 85% by the 2000 cycle. Now this capacity drop is very huge in terms of batteries. According to IEEE standards, when the capacity retention drops to around 80%, it is considered replaceable because it shows that the battery kinetics are rapidly deteriorating. So we know that why this happens is this sulfide is irreversibly being oxidized to sulfates. So there is no depassivating agent at all to remove the passivating layer. So that's what's happening with this additive. But interestingly, when we introduced this selenium, we found very, very good results, extraordinary results. So even when the selenium is present in the electrode, the capacity retention at the 2000 cycle is around 96%, which is quite exciting. And this happens because the selenide, it is serving as an inexhaustible reserve of depassivating agent due to its electrochemical reversible nature. And similarly, when the selenium is present in the electrolyte, we again see good capacity retention. I'm still cycling these cells and taking data on them, and they're performing really good in terms of that. And at last, I just wanted to compare the polarization curve of these life cycles for the 3 electrodes that I was studying. And as you can see here, for all the 3 cells, that the polarization curves compared to the very first cycle I have to the very last cycle, that is the 2000 cycle, the polarization curve has not significantly changed. And you have to understand that when I say 2000 cycle, it equals to around 8,000 hours of continuous cycles of charge and discharge, which equals to around 1 year of running of these cells. And these cells were able to maintain their polarization curves after going through so many changes. And this tells that how robust these electrodes are, and so can serve as a great potential for large-scale energy storage devices. And just to summarize just to summarize the talk, the goal was to find an alternate additive that could serve as a depassivating agent without compromising the life cycle of the electrode, and selenium serves the right purpose for that. It was found to be electrochemically reversible. The performance of iron electrode did not significantly change in terms of formation capacity or discharge rate capabilities, and the life cycle studies confirmed that selenium containing cells outperforms the sulfide containing cells. And at last, for the acknowledgement, this project was initiated by Dr. Sri Narayan. He was my mentor, but we lost him to cancer last year. But I'm grateful that I had the chance to learn such good chemistry from him. And of course, my now supervisor, Dr. Surya Prakash, who has been a great motivation and support throughout this completion of the project. I would also like to extend my gratitude towards my lab mates and the Local Hydrocarbon Research Institute and the Wrigley Institute for Environment and Sustainability for the funding. Thank you.
Thank you very much, Yashvi.
Thank you.
So actually, we'll skip the questions because we are running short of time. We'll go to the next presenter from
Okay.
University of California, Santa Cruz. He's an undergraduate, Carlos Garcia Guerrero. And he will be talking about testing the sensitivity in Saccharomyces cerevisiae to splicing inhibitors in humanized branch point binding pockets. Thank you. Go ahead.
Yeah. Thank you for coming in and for the introduction. So my project is in conjunction with the guidance of my PI Manuel Aries and with guidance from Melissa Jerica or Dr. Melissa Jerica from the Center for Molecular Biology of RNA or the RNA Center. And so let me just get into it. A little background on RNA chemistry and structure. As we know from our introductory biology courses, DNA is how we give the transport like proteins and the coding for proteins and genes. And the way that's done is through transcription of the DNA, right? So it has to get transcribed through this process called splicing. And so pre-mRNA is essentially the molecule that's a single-stranded that has these intronic and exonic regions. And the intronic regions are usually the ones that don't have any protein coding importance. And so the exonic regions are the ones that hold the proteins or the coding for the proteins. And so the Aries lab is interested in the spliceosome basically. And they look at these things called small nuclear ribonucleic proteins, these things that make up the spliceosome complex. And so that's where my project is focused on. And essentially what the Aries lab wants to know is how does the splicing occur in humans? And in order to answer these questions, they use a model organism called Saccharomyces cerevisiae, which is just baker's yeast. And that's kind of where my project is. And the specific SNRP that I'm interested in is the branch point binding pocket. And it's this protein right here. And so in the Aries lab, they were able to humanize the yeast, which essentially means they were able to take some of the human protein regions and edit the yeast protein and basically get a strain that had these protein coding regions from the human version and have it be expressed in this yeast. And so now this yeast was able to get drug sensitive and be inhibited by these splicing inhibitor molecules. And so that's kind of where my project now takes off from this one paper done by now Dr. Ortiz Hunter. And so he was able to make this strain and show that this can be targeted by these splicing inhibitors. And the gene that I'm particularly interested in is the RDS3 gene in yeast. And so the homologous version of that gene is gene or protein is PHFA in humans. And so this protein is interesting because it was able to be covalently inhibited by these splicing inhibitors like PLAD-B, which I'll get into in the next slide. So a little background on splicing inhibition. You can essentially stop splicing by using these molecules like FR9-1464 or spliceostatin A. There's some other analogs right here, but there's basically three families, which are the phthalate and spliceostatins, the I can't say the name, but it's platinines and herboxidines. And so these can all inhibit splicing. And the reason it's interesting for us is because you can essentially stop certain disease genes by using these drugs. And so a lot of anti-cancer research is being done on these kind of drugs and the analogs of them. And potentially the research that I do in this lab can contribute to some knowledge in that. And so in the Aries lab, they were able to show inhibition of this strain or OHY001 or HSH155. And so H155 is the yeast gene that they made to look more like the human version, and they were able to show inhibition of this gene over time and concentration. So as you can see, it's kind of a little dark right here, but in the future, in other slides, I'll show it more. And so the difference between spliceostatins and dallostatins is this ring right here. And this is kind of the focus where these covalent interactions in the yeast gene or the spliceosome occurs. And so my experiment kind of wants to answer these questions of what modifications can we do to RDS3? And are there any modifications that will give us any insight on this residue that can covalently bond to these splicing inhibitors? And so that's where this paper is where I got this these files to look at the cryo-EM structure. And so this is the exact residue in the pink RDS3 gene that I'm interested in editing. And so this is being done in a yeast. However, this covalent interaction was only shown in the human spliceosomes. And so I'm now trying to show that this can be studied in yeast and you can edit it and get some more insight. And so some of the mutations that I was considering in our project was doing a cysteine-26 to serine mutation. So it's changing that sulfur to an oxygen, or a cysteine-26 to alanine, which is making it a methyl. And so I have aspartic acid here because it will be of note later when I talk about the actual mutations that I got. And so some of the questions that I've had for this project is what other mutations or residues may contribute to splicing inhibition in the branch point binding pocket? And in order to do that, we kind of have to look at the mechanism of how this covalent bond forms. And so this diagram kind of shows the residues that may contribute to the covalent formation of this bond right here. And once again, this is occurring in the human version of the protein of the spliceosome complex or the branch point binding pocket. And that region is important because it's where the sites for splicing occur. And so I'll kind of move on ahead. And so this is the exact region that I was talking about that was having this covalent interaction. And this is spliceostatin A. So it's very similar to dallostatin and not too similar to 5B. And so a little insight on some molecular tools that we used to edit it was to do CRISPR editing in yeast. And so I was able to first generate a plasmid that can have my guide RNA and help us basically target the RDS3 gene in yeast. And this was a very simple schematic of what I did in order to get these mutations. And I guess the hardest part at first was constructing a plasmid, since it was a little hard to linearize, basically make this into one, basically cut this plasmid backbone and then do this insertion through Gibson assembly. But once this was made, I could then start doing some yeast transformations with this plasmid and use these oligo rescue fragments that will carry the mutations that I desire. And so some of the mutations that I got this spring was these two mutations. And these are the only ones of note because I was not able to modify the gene to the desired residue mutations. And this mutation occurred in a control strain. And this was promising since it did show that cysteine could be. However, in the humanized strain, I was having a very hard time modifying it. And there's a lot of, we have some ideas why that was the case. RDS3 is a very conserved protein. It doesn't change residues through various organisms. And the yeast protein and the human protein are basically, they're homologous. And so that cysteine may not be changed as easily as we thought. And so this is some data that shows that we mutated those regions. And so this is the cysteine-26 codon that we mutated. And this is here in the browser. As you can see, it's a GA mutation, and so this changes it to a aspartic acid. And the one over here is a single nucleotide change that changes the splicing to aspartic acid. And so this mutation may actually provide some insight, given we know the role of this glycine in the RDS3 gene. But for now, we kind of have pivoted to some other questions that we can do with the current strain that Ortiz was able to generate. And so this strain is once again like able to be inhibited by these molecules. And so this is kind of what occurs in the spliceosomal complex. And SF3B1 is the human version, and PHFA is once again the human version of the spliceosomal complex proteins. But the RDS3 is the homologous of this one. And this is the cysteine 26 mutation that I was talking about earlier. And the difference between fludarabine and the spliceostatins are kind of shown right here, where the fludarabine can't really make this covalent bond, while spliceostatins can. And so that's kind of what Ortiz was able to get up to. He was not able to show these covalent interactions in his paper, but he was able to show inhibition with fludarabine. And so now I've been kind of trying to test other inhibitors, and this is a RT-PCR gel that shows inhibition of splicing in the yeast strain that he generated, and the specific intron that he's looking at is of the first intron of MAT-A1 gene, and so it's the gene of interest that we want to look at for at least these splicing inhibition experiments, because it's one of the first genes that gets spliced in the cell, in the yeast cells. So I was, these last couple months, I was replicating these fludarabine inhibitions. So this is my replication of that experiment that Ortiz had shown in his paper. And DMSO is the control that we use. And as you can tell, there's no splicing that occurs with DMSO, since it's not a molecule that will have these, that will not fit in to those spliceosomal complexes. And this is the spliced and unspliced that is occurring after a certain amount of time when once inhibited by these drugs. And this is kind of the stuff that I did in order to get this to work. You start with a 50 ml culture in this kind of media, and you want to usually do 1 to 5 micromolar inhibitor under less than 1% DMSO in order to not affect the cell. And in the way we take time points, basically how we freeze the cells in time is using very cold ethanol, which is usually in dry ice. And then we just do some RNA extraction and RT-PCR in order to visualize the splicing that occurs. And so the thing that my PI was kind of wondering and tasked me to do was to see if by washing out the media that this yeast is in, can you recover splicing? And so that's one of the questions that I was answering with these experiments as of recent. And so what I did in here, different from the paper that they were able to publish, was that after 4 minutes, I took the culture that I had remaining, the remaining liquid culture, and then I spun it all down, spun the cells down, and then removed the liquid media culture, and which included the drug. And then I resuspended it all in fresh media and continued taking time points to see if you could basically wash out the drug and recover splicing, which this initial gel was proving, since you can see that it's splicing at first, and then it gets inhibited after a couple minutes. And then you can still see that it's still splicing, but after the first wash, it's basically stopped splicing, right? And then it starts recovering again. And eventually, over time, you'll probably see that it returns back to the splicing, this spliceosomal complex. And this is kind of what I show in this second attempt, where you see I start inhibiting it Unfortunately, I don't know what happened with my 8-minute. It just kind of didn't show as much splicing inhibition, or yeah, splicing inhibition as my previous gels. But you can see that it's kind of half and half with the unspliced and spliced products. But over time, you do get recovery of splicing. And so this was a good sign that Plaid B isn't doing this covalent interaction as theorized. And this is occurring in the yeast. So my next kind of questions are, can you do this in with Thal A? And so that's the kind of experiments I'm doing now, testing using a different inhibitor and seeing if it follows this pattern or if it completely kills the cell and you won't see any more splicing. And these are some of the plates that I ran to show that it's at 8 minutes, it's not growing any cells. But after you wash it out, the drug, the cell can recover and basically grow back again. And so that's what these yellow ones are. And so yeah, moving forward, I will try to continue trying to edit this gene, since it's really interesting how this regulatory drug sensitivity can kind of control a lot of this inhibition, and potentially go into new directions of modifying the gene, either choosing a new residue or a new method of modification. These modifications may actually cause alternative splicing, and so that's another one of the questions that my PI is wanting to answer, and what other mechanisms of splicing can occur. And I will continue doing these inhibition studies with other inhibitors like Thal A, and that's where Dr. Melissa Jerica was able to provide these other inhibitors, since they're quite pricey. And yeah, maybe potentially use some of the mutants that I generated previously with the glycine 28 mutation and see if that actually changes anything. And so these are some of the references that I use. So that's the paper that I'm referencing most of my work from. This is a paper that kind of discusses these drugs and how they're useful for maybe modulating cancers and drug-resistant cancers, right? And this is the paper where they show this covalent interaction from for these splicing inhibitors. And so, yeah, I just kind of want to acknowledge my lab, my PI, NL Aries. Yeah, special thanks to Ortiz Hunter. He was able to kind of help me out with a lot of these splicing inhibition protocols, even though he's not at this school anymore. And then once again to Melissa Jerica for providing drugs for these experiments and for these funding institutions. Yeah, so any questions?
Thank you. Carlos, take a look at the chat and answer the questions via chat, because we don't have time. We'll go to the next presenter, an undergraduate student from University of Washington, Michael Rosen. He'll be talking about capturing angular momenta in high-resolution rotation vibration spectra. Over to you, Michael.
Hi, thank you for the introduction. As was mentioned, I'll be talking about capturing angular momentum terms in high-resolution rotation vibration spectroscopy, and this will be theoretical work. But before I get into that, I first want to talk about, if I can get into PowerPoint. So I first want to talk about a kind of lower level introduction. So I want everyone to imagine that they're an undergraduate chemistry student. And in your undergraduate, you will take a physical chemistry lab. I did this past fall, and when I took it, I was given a mixed solution of hydrogen chloride and deuterium chloride gas, and I was told to take a vibrational spectrum. And in the spectrum, I noticed that there are 4 sets of peaks corresponding to the fundamental and overtone vibrations of the 2 different species present. And then I zoomed in onto one of these bands, which corresponds to just one vibrational transition. And this encodes a lot of rotational detail. So upon zooming into this rotational band, you can see this very nice Boltzmann-like shape. And in this lab, you will very clearly define, or you will elucidate all of the details of the spectrum through investigating the P branch, which corresponds to changes in the angular momentum quantum number of -1, the R branch, which corresponds to changes in the total angular momentum quantum number by +1. And if it were to be present, which it is not for a diatomic, you would also investigate the Q branch, which corresponds to no change in the total angular momentum quantum number. And this completely describes the behavior of a diatomic molecule. So upon finishing this lab report, I walked out of the classroom and up a flight of stairs and into the research office, where I was given a spectrum of dimethyl sulfide. And this is a vibrational spectrum. And immediately we can see that there are a lot more details, but we can pick out some rotational bands that are present. If we again zoom in onto one of them, we will see a lot of detail that looks similar to the normal P, Q, and R branches for a diatomic, but now there is some additional detail due to the fact that this is an asymmetric rotor. But there is still more detail than we would expect to be seeing. So if we again continue zooming in onto this spectrum, now just to a span of 3 wave numbers, we see even more detail present, and we can continue zooming in down to the space of just one of these peaks, which has a width of about 7/1000ths of a wave number. And this spectrum was collected by the collaborators of David Nesbitt. He is at CU Boulder. And the goal of this work will be to fully describe these super high resolution peaks and to understand the full behavior. And kind of as a spoiler alert, this behavior is due to the fact that these methyl groups can rotate internally. And so to begin describing this, we want to work with the quantum mechanics of the problem, which involves writing down a Hamiltonian, which that in and of itself involves writing down the kinetic energy operator. So to do so, we need to have 3 descriptors. We need to describe the free space tumbling of the molecule. For something like water, this would be the full picture. And the way that we do that is we write down a Hamiltonian that has a sum of different angular momentum terms about 3 different axes times some coefficient. And when I talk about these axes, I'm talking about something called the principal axis system of the molecule. And this typically reflects the symmetries of the molecule. So you can see for something like water, we have one of our axes as a HOH angle bisector, along with an in-plane and out-of-plane axis. And then these coefficients that go in front of these angular momentum terms are called rotational constants. And these wrap in the moments of inertia for rotations about any of these 3 axes and tell us how difficult it is to start rotating around any of them. For dimethyl sulfide, the next part is going to be describing 2 torsional angular momentum in the methyl groups, or momenta in the methyl groups. And so I've added some arrows here so you can see what these torsions would look like. They correspond to just spinning these methyl groups around the CS bond. So again, what we can do is write down a torsional term for the Hamiltonian, which wraps in an angular momentum projected about the CS bond, times some rotational constant for that rotation. The next step is going to be combining these 3 parts into one Hamiltonian. And to do so, we need to rewrite everything in terms of a total angular momentum term. And to do that, we can add together our 3 angular momenta like a vector, where we have a fancy plus sign because now we're dealing with quantum mechanical objects, so we need to use a bit fancier math to achieve our actual summation. And then we'll continue doing what I call mystery math, which is just kind of a shorthand for lots of classical mechanics. That's very difficult to do and takes pages upon pages to work out. But if we do that, our Hamiltonian takes a form that looks like this. And this, at first glance, looks to be a bit of a mess, but we can separate it into 3 individual terms. The first one is solely rotational, and it mirrors what we have up here for free space tumbling. The very last set of terms is solely torsional. So we can see we have these P1 and P2 terms, and then a coupling, and then a potential that is tied to the torsional coordinate. And then we have what's called Coriolis coupling, which tells us how these internal rotations couple to the overall rotation of the molecule. So the next step is to look deeper into the Hamiltonian, and I've just rewritten it up here at the top, along with the corresponding colors. So in this Hamiltonian, we can imagine writing out our basis functions for this Hamiltonian, which I've denoted as psi, as a composition of 3 separate sets of basis functions. 2 of them will correspond to the torsions, 1 set for each of them. And then we will have this third set of basis functions, which correspond to the rotational terms. And in this talk, I will not be explaining or diving too deep into these rotational terms, since they've been discussed pretty well at length in the past and are very well understood and have been implemented in software packages such as pgopher. But the more interesting term to us is going to be investigating this torsional Hamiltonian term. And then we will just assume that this coupling term comes along for the ride and will work itself out once we throw everything together in the end. So pulling up the torsional Hamiltonian, where I have now substituted in the actual form of the potential, what we can do is we can solve it through the linear variational approximation. And this will allow us to investigate the energies and the wave functions for this. In this talk, the wave functions are not as important. We could plot them out if we wanted to, and they will get used for evaluating intensities. But for us right now, the main thing that will be interesting is to investigate the energy spectrum. So we can plot that out, and for the torsions, we'll find that we have a nearly degenerate or nearly 9-fold degenerate ground state, followed by a first excited state that is nearly degenerate 18-fold, and we'll continue seeing this pattern. And the ground state lies at about 173 to 178 wave numbers, and the barrier for the rotations is about 670 wave numbers. So you can see we have some embedded vibrations that are below that free rotation barrier. So the next step to describe our spectrum is going to be talking about how we can calculate the intensities. And when thinking about that, the main important term is going to be something called the line strength, which describes how our lower state wave functions couple to the upper state wave functions through an interaction of the dipole moment of the molecule and the external electric field of our laser, which I just for shorthand call red Q hat to signify that there is a lot of terms that are being wrapped in here, but it's nice to just be able to put one letter instead of a whole sheet of terms. So if we instead describe this line strength using the language that we've developed so far, where our wave function is going to be described by a torsional wave function and an angular wave function that are being coupled together. And we then put that into the form of this expression down here. It looks a little bit nasty, but we can immediately start simplifying it by thinking about the physical system that we're looking at. So for dimethyl sulfide, these torsions won't affect our dipole moment that much. You can imagine spinning these groups around because of the symmetry of them doesn't affect our dipole moment. So what that means for us is that these torsional wave functions, when this Q hat operator operates on them, they won't be affected. So we can immediately just rip them out to the front of our expression, and we'll end up with a separation of 2 terms here for our line strength. The first one is going to be called the Frank-Condon factor, and this is something that is very commonly used in electronic spectroscopies. And then our second term here is going to be an angular momentum only line strength expression. And this, again, is something that is well understood and is already implemented in a lot of rotational spectroscopy packages. So we can continue to investigate this term a bit further. And if we treat only this term on the right side, if we were to evaluate only a rotational spectrum for dimethyl sulfide, we will obtain something that looks like this. And this begins to mirror the spectrum that we had at the start of this talk, the experimental one, but it looks very spiky, but it is not as high resolution as we need to fully describe what's happening. So that's where this term on the left side comes into play. And if we evaluate this for just one of the peaks on this side, in this case, the J equals 0 to 1 transition for our rotor, we will see 3 sets of peaks where we typically would only expect to see 2 peaks. And we can map out what's occurring here. So for these peaks at plus and minus 0.75 wave numbers, we see that they have shifted around just a touch, and they have also split apart with a second peak picking up some intensity. And then simultaneously, we have picked up a new set of peaks here just next to zero wave numbers at the center of one of these transitions. And these correspond to transitions between those nearly degenerate ground states. And so the future plan for this project is going to be evaluating a spectrum that couples together these two sides of the line strength. However, the problem with that as of right now is this is incredibly computationally expensive. Even just attempting to include one more set of rotational transitions in this evaluation yesterday, I almost overwrote my entire hard drive with new data. So the next step, or the immediate next step, will be coming up with some nice mathematical simplifications to this formula that will allow us to continue investigating it. And so I'd like to acknowledge the McCoy Group, which I am a member of at the University of Washington, who have been instrumental in aiding me in figuring out all of this stuff. I'd like to acknowledge the Xanthias Group, who is our sister theory group at the University of Washington, for putting up with my group meetings and all of the details that I discuss. I'd like to thank Professor Edwin Seibert from the UW-Madison, who is working on the skeletal vibration side of this project. I would like to thank Professor David Nesbitt from CU Boulder, who is working on the experimental side, and I would like to thank the University of Washington Department of Chemistry ChemStar summer stipend for providing me funding over the summer. And as anyone in the McCoy Group knows, at the end of my talks, I like to also acknowledge my dogs, and I have provided you with a lot of pictures to take a look at them. So that is the end of my talk, and I would like to open the floor for questions. Thank you.
Thank you, Michael. Since we are running late, we don't have time for any questions. We may answer questions through chat perhaps sometime. Thank you. The next speaker is undergraduate from Arizona State University, Jordan Begay, and he'll be talking about simultaneous spectrophotometry applied to 3-tablet formulation of human immunodeficiency virus medication containing amitriptyline, tenofovir, dispropoxil,
Krishna, I don't show that Jordan's,
ribavirin hydrochloride. Thank you. Go ahead.
Krishna, I don't show that Jordan's in the meeting.
Oh, George, it's a meeting?
He's not, no, they're not here.
It's not in the
Oh, we
meeting? Okay, we'll go to the next presenter then.
Mhm.
The undergraduate from DePaul University, Rahman Arif, and he'll be talking about computational molecular docking simulations of aptamers targeting CD30 in the treatment of Hodgkin lymphoma. Over to you.
Hi, thank you so much. Unfortunately, my camera isn't working today. I don't know if that's a issue, but I'll present without it, I suppose.
Hello.
Hello.
Hello?
Yeah.
I'm so sorry to cut you off. My hands were up, but I think you didn't notice. So I just want to ask a very quick question.
Oh, you have
And
to
also
put the
make an
questions in the
update.
chat.
Okay, all right. So sorry.
Okay, I'll share my screen.
Okay.
Okay, so the title of the research I conducted is titled Computational Molecular Docking Simulations of Aptamers Targeting CD30, which is a protein receptor, in the treatment of Hodgkin's lymphoma. So just to start, a few facts about Hodgkin's lymphoma is that every year in the US, there are 9,000 cases reported, and that's just in the US alone. And without insurance, it costs $200,000 to treat. Some common risk factors of Hodgkin's lymphoma include.
Hi, Riemann, your audio is not coming through on our end.
Audio is not coming properly, yeah.
Can you hear me now?
Sounds very choppy.
not exactly sure. Is it really choppy? I can try and reset my computer. I may be having internet issues as well.
Okay. Can you work on that, and we'll come back to you then later for your presentation? Probably we'll move on to the next presenter. Is that okay, Daniel?
Yeah, absolutely.
Okay, so from a graduate student from UC Irvine, Caitlin Dole, she will be talking about tuning the helical structure and properties in the all inorganic 3, 6, 7 class of materials. Can you go ahead, Caitlin?
Hello, can you guys all hear me?
Yes.
All right, perfect. So today I'm going to be talking about what was just mentioned, a new structure in this 367 class of materials, and I am in the Argelia group at UC Irvine. So helices, as most of us know, are extremely common in biological molecules and other types of molecular systems, and have recently become of a lot of interest due to some really interesting phenomena that they exhibit. And so one that our group is particularly interested in is chirality-induced spin selectivity, or CIS. And this is a property in which chiral molecules can selectively transport electrons based on the handedness of the helix and then the spin of the electron. So for example, a left-handed helix would selectively transport spin-up electrons. And this has the potential to be used in various technologies, like in creating spin filters or in spintronic devices. However, to utilize this property for technological applications, we need to find structures that are not biological, that are in these extended inorganic lattices. And this is because extended inorganic lattices have heavier elements, which improve cis effects and have longer range order to be utilized in different technological applications. And so before we can even think about cis, there are very few known helical materials in extended inorganic lattices. So these are basically the only two known classes of helical freestanding inorganic solids. One is just based on crystalline tellurium, the element, and the other is the structure tin iodophosphide. And so these materials are both 1D van der Waals materials. Meaning that they can be exfoliated into few nanowire thick chains or even into single chain materials pretty easily while retaining their crystallinity and long range order. They also have an indexable set of tunable helical parameters that can be used to directly modulate the chirality-induced spin selectivity effects. However, neither of these materials are very modular. Only one structural analog exists for each. And so in extended lattices, the main way to modulate the helical structure would be via isovalent substitution or alloying, meaning that these materials, we fundamentally do not understand how helicity in the solid state looks like, and how we can use these materials to influence the structure and properties. So indium selenium iodide is a recently discovered helical all inorganic solid, and this material is built from these indium selenium 3 iodine quasi-tetrahedral building units that are connected by bridging selenium atoms to form the overall structure. And these materials consist of 3 concentric tetrahelices. This is the indium tetrahelix shown here. And this is just a linear stacking of face-sharing tetrahedral units that form a helix. Unfortunately, indium selenium iodide is overall achiral because adjacent chains along the X and Y crystallographic axes are of opposing handedness, crystallizing in the centrosymmetric I4-1/A space group. However, as I mentioned, because this is a 1D van der Waals material, we can exfoliate this down to a single chain, just using Scotch tape, for example. And recent work in our lab has looked at the substitution of indium with gallium, and we can see a clear change in the helix parameters. The long axis of the unit cell increases almost 5-fold, and the material becomes non-centrosymmetric, crystallizing in the CC space group. And so non-centrosymmetry, while still being achiral, does give rise to various nonlinear phenomena like piezoelectricity and second harmonic generation that are now opened up within this class of materials. And so the main goal of this work is to just fundamentally understand how composition influences structure and properties in the 367 class of materials to eventually be able to use these for chiral spintronic applications. And so my first goal was to look at the influence of the chalcogen site on the helix by substituting selenium with sulfur to create gallium sulfur iodide. So this material can be synthesized through a pretty standard melt synthesis where we put elemental precursors in a glass ampule and seal it under vacuum, and we heat it at 500 degrees Celsius using a heating profile for 6 days. And we can access pretty large, pretty long single crystals that clearly have a one-dimensional needle-like morphology. Then I performed a detailed structural characterization of this material to look at its crystal structure and exfoliability. And so we can see that this material crystallizes in the non-centrosymmetric P4 bar space group, which we found through single crystal X-ray diffraction, and that it does retain its helical structure and looks pretty similar in the single chain to the gallium selenium iodide material. Of course, again, we can grow these crystals very long, and these materials can also be exfoliated using Scotch tape into nanowires, where we have been able to find one that is only 11 chains thick of gallium sulfur iodide. These materials do retain their crystallinity at these size regimes, and we can see through high resolution transmission electron microscopy here that the helical motif is retained at the atomic scale. So after looking at the structure of this material, I then wanted to look at how the helix parameters changed between gallium selenium iodide and gallium sulfur iodide. And so I'm just going to talk about the one that was kind of unexpected, and that was when we looked at the cross-section of the helix. And so what we expected, because we're substituting in a slightly smaller element, selenium with sulfur, we expected all of the cross-sections to slightly contract. And so while we saw that for the chalcogen site shown here, where the blue shows gallium sulfur iodide and the red shows the selenium one, for the gallium and iodine cross sections, we found that instead of contracting, they actually distorted. And so we were able to fit these cross sections to a shape known as a Fernandez-Guasti squircle, which is a cross between a square and a circle, with just one extra parameter in the fitting equation, S, that tells you how square or how circular you are. And so gallium sulfur iodide lies appreciably between a square and a circle, with the S of the gallium and iodine being around 0.65. To investigate the origins of this distortion, I then looked to do a bond angle analysis as well as do some density functional theory calculations. And so the bond angle analysis kind of told us why these materials are so much more modular than the other known classes of all inorganic helices. And this is because these metal chalcogen metal angles from these corner sharing tetrahedral building units are actually extremely able to handle the strain of various elements because they can move around and the angles are much more flexible. And so from selenium to sulfur, we see an expansion of these bond angles. And this incorporates the strain that's induced by this smaller sulfur element. From the bond angle analysis, or excuse me, from the DFT calculations, we found that if we take the bulk structure of circular cross sections and do an energy minimization calculation, we end up with the squircular distorted cross sections. However, if we take a single chain in a vacuum of the squircular cross section and energy minimize it, we end up with an isotropic cross section. So this really told us that the origin of this distortion actually has to do with the interchain van der Waals interactions, and that these interactions between chains play a major role in the crystal structure and packing of these materials. Finally, we wanted to look at some of the properties of these materials. First, to confirm unequivocally the non-center symmetry of the structure, because that can be really difficult to figure out through just single crystal X-ray diffraction, and to see the potential of these materials as nonlinear optical solids. And so we probed the second harmonic generation response of these materials, which is a nonlinear optical property in which 2 photons of an incident wavelength are combined within your crystal, and a photon at half the wavelength or double the energy is emitted. And so the band gap of gallium sulfur iodide is 3.69 eV, shown through diffuse reflectance spectroscopy, which equates to 336 nanometers, which is well in the UV region. And so we can potentially do second harmonic generation into the deep UV using gallium sulfur iodide. And through SHG microscopy shown in these images, we do confirm the SHG response of gallium sulfur iodide. So to conclude, and some future outlooks of these materials, gallium sulfur iodide is a new helical 1D van der Waals material with non-center symmetry that gives rise to second harmonic generation in the structure. And this virtually unexplored 367 class of materials has a rich phase space to explore the effect on the structure-function relationships in these helical solids. And so future work in this project is looking to expand the library of this phase space, as well as explore other properties like birefringence and second harmonic generation on these materials. And so with that, I'd like to acknowledge my group, as well as the funding, various funding sources for funding this work, and all of my collaborators. And thank you very much for listening. I'd be happy to take any questions in the chat.
Thank you, Caitlin, very much. We'll have any questions, you can answer it in the chat. Thank you. The next speaker is, shall we move on to the next one, Daniel? It's an undergraduate student from the University of Washington, Dan Lawton. Will be speaking about simultaneous simulating the vibrational spectrum of the formic acid dimer using 2D DVR.
Thank you.
Go ahead.
Sorry, I'm in the process of sharing my screen right now.
It's okay.
Everything looks good on this end.
Hello, everyone. Like you said, I'm Dan Lotan. I'm a member of the McCoy group at the University of Washington. I'm a fourth-year undergraduate. So the McCoy group is a vibrational spectroscopy group. You can see one of the molecules that is currently being studied on the screen right now. I've been looking at one of the specific features of this molecule. I've been looking at these double hydrogen bonds that is holding the cation together. Now, if you want to study a hydrogen bond, it's been shown that a great way to do that is to look at its vibrational spectrum. And you can see an example of one of those in the bottom left right now. Specifically, this is the one where the length of this carbon CH2 chain is 4 carbons long. So something interesting that you can note is that as you vary the length of this carbon chain, the distance between these carbon atoms changes, and it looks like there's a relationship that forms between the distance between these carbon atoms and the frequency of the vibrational spectrum. The frequency is the x-axis of the graph that you saw on the previous slide. So my goal is to see whether this change in the CC distance is directly what's causing the changes in the frequency, or if it's some unrelated effect, and this is correlation, not causation. So if you want to study just the effect that this carbon-carbon distance has on the vibrational spectrum, really what you want to do is you just want to look at this double hydrogen bond feature, because this is a complicated molecule. There's a lot of other stuff going on. So one way to just isolate the properties of interest is to use this formic acid dimer as a toy system, because it gets rid of all the other features and just isolates that double hydrogen bond feature. Now, there's no way, you can't actually vary the carbon-carbon distance itself through any kind of physical experiment. So we're going to have to use a computational approach. And if we're going to do something like that, we need to understand how you actually calculate a vibrational spectrum. So intensity is the y-axis of a vibrational spectrum. And like I said, frequency is going to be your x-axis. So the physical phenomenon that the vibrational spectrum comes from, you can see at the bottom, the molecule is in some vibrational state. It absorbs a photon of some energy with some characteristic frequency, and it gets bumped up to some hot, excited vibrational state. So there are 4 quantities you actually need to calculate the intensities. First, you need the photon's frequency. You need the dipole moment matrix of the molecule, and you need the actual initial and final vibrational wave functions. By wave function, I know not everyone here is probably that familiar with quantum mechanics. The wave function is like a probability map, where if it's in a ground state, it's probably, hydrogens are probably going to be in some specific area. When it's in an excited state, the hydrogens are probably going to be in some different arrangement. Anyway, these are very mathematical quantities, so we need some way to define the dipole moment and some way to define the wave functions. The way that I'm doing that is using this quantity called, this basis called DVR. So basically, I'm going to need to find 3 quantities. First, I need the dipole moment matrix. Obviously, that's going to go straight into it. And I also need the kinetic and potential energy matrices. And this is going to get you Hamiltonian, which you do linear algebra on to actually get the eigenfunctions. These are the wave functions, and the energies, which gets you your frequencies. What DVR specifically is, you can see an example of a DVR matrix in the bottom right. I've used a simple system as an example for this, just a ball on a spring. If you move the ball to the left or right, you're going to increase its potential energy. Basically, the special thing about a DVR is that these rows and columns correspond to discrete positions in space, as in this row would represent it at this x equals -1 position, for example. I'm not going to go into the specifics of it, just know that the rows and columns represent distinct positions. Now, why is that important? Why am I doing this? Basically, this is going to make it extremely easy to actually build these matrices for potential energy and for dipole moment, because these quantities are just purely functions of position. So if these rows and columns correspond to distinct positions, then when the rows and columns represent different positions in space, there's no overlap between them, then the entry is just going to be 0. And when they represent the same position in space, you just need to calculate the potential energy or the dipole moment at that specific position. Now, this is, for something like kinetic energy, this is going to make it a lot more complicated to actually go through the math and find each entry. But the thing about kinetic energy is that there are tons and tons of formulas and tons of models that you can use to actually get kinetic energy. And you can see that it actually comes out to a relatively simple equation. But basically the idea behind DVR is that there's no simple equation or model or something like that you can use to get these potential energies and these dipole moments. You have to physically go through and either measure them experimentally or use computational software to find them. And for kinetic energy, there's always some kind of high level math that you can do to actually get your kinetic energy. So by using DVR, we're making the extremely difficult parts much easier. So from this natural workflow to actually create these vibrational spectrums is created. Basically, first you need to actually go through and calculate the kinetic potential energies and the dipole moments at specific positions for this project. That means specific OH bond lengths, and use those to create your potential energy and your dipole moment matrices. Next, you make your kinetic energy matrix. You add your kinetic and potential energies to get your Hamiltonian, and you perform linear algebra to get your frequency and your wave functions. That gets you everything you need to go to the last step and actually calculate your spectrum through. So we can now actually apply this to the formic acid dimer and see what the spectrum looks like. So remember, the two things we need is potential energy and the dipole moment. And so this is what the potential energy surface looks like. And I mentioned before that the quantities I'm using are the OH bond distances. These aren't entirely true. What I'm actually doing is I'm looking at how the top hydrogen is displaced from the center of the oxygens and how the bottom hydrogen is displaced from the center of the oxygens. So in each of the different quadrants, you can see roughly where the hydrogens are in space. And you'll notice that there's actually a lot of redundancy in this potential energy surface. A lot of because this molecule is so symmetric, a lot of these configurations are basically the same, but the molecule is flipped. That's why there's, for example, this double well that you see. Dipole moment is a little bit more complicated. Potential energy is just a value, while dipole moment is a three-dimensional vector. So you need to get the X component, the Y component, the Z component for each configuration, and you need to define your axes. For this molecule, it's made a little simpler by the fact that formic acid is a completely planar molecule. So you know that whatever component is outside the plane of the molecule is always just going to be 0. So we can just define that as the Z component and define our X and Y axes like so, and get these dipole moments. And from this, like I've said, that's all you need to plug those into your workflow and actually get your spectra out. So this top plot is the actual intensities versus frequency data. And then we do what's called a Gaussian spread to actually convert that to what it would look like. You remember that this is what when you actually measure it in a lab, it's not just this stick plot. It looks more like this on the bottom. So it looks like it works well for the regular formic acid, but we're looking at how this CC distance is going to affect the spectrum. So now we're ready to actually extend this. Before, when I actually was building it, the formic acid dimer using computational software, the CC distance that for the minimum energy configuration was 3.85 angstroms. That was the value I used for the previous spectrum. Now I'm going to extend that to 3.95 angstroms, 4.05 angstroms, and see how the frequency of the peak is affected. So what do we actually see? Well, the frequency is definitely decreasing with increasing CC distance, and it is an extremely nice relation. You can see the specific spectrum on top. You can see the relation on bottom. Looks very nice. So I showed you before what the experimental values look like. Unfortunately, we don't really expect this to match 1-to-1. These are different molecules after all, and the actual molecule that was measured is a lot more complicated. However, if you actually take these two plots and put them on the same graph, it's kind of remarkable how well of a relation this actually has. So this suggests that is definitely from what's been collected so far, it definitely looks like the CC distance is what's legitimately causing this, because I basically took all the other factors out that could have affected it. So what needs to happen from here? Well, I've only used 3 points in my graph. I definitely would need to collect more data for that. 3 data points isn't enough to say decisively that this is what is happening. It would also be nice to you might have noticed that I was using CC distances that are a lot bigger than the ones for the molecules that was actually measured, because the different molecules, they have different natural CC distances. So it would be nice to shrink that formic acid down instead of extending it, and make sure that it actually matches these orange points that were measured. And then I can also look at the trends in the intensities rather than the y-axis, rather than just trends in the frequencies. I'd like to thank everyone in the McCoy group for their help. You can see them pictured here, except for Andrew Webb, who doesn't have his picture yet. Yeah, thank you everyone for listening to my talk.
Thank you very much, Dan. We will go to the next presenter, an undergraduate student from Fairleigh Dickinson University, Antonio Campo. We'll be talking about green method to prepare pluripotent nanocomposites based on renewable sources. Antonio?
Hey everyone. All right, so today I'm going to be presenting green methods to prepare. Oops. Green methods to prepare pluripotent nanocomposites based on renewable sources. I'm not going to read everything here, but basically what we're working with is creating nanoparticles using sustainable biopolymers, using GRAS substances, which means generally recognized as safe. So the first component of our nanoparticles is zane and lupulon. Zane is a proline-rich protein found in corn. It has a high content of hydrophobic amino acids on the surface, making it insoluble in water. We chose this because it's renewable, biodegradable, inexpensive, and safe to use for humans. It's also good as a topical delivery system because of its high biodegradability, biocompatibility, superior binding ability, moisture attractor, and its ineffective absorption by the targeting cell. The next component is lupulon. It's a mixture of components and lupulon, colupulon, and adlupulon, which is extracted from the female hops plant. It's a known antioxidant, antimicrobial against gram-positive bacteria, anti-angiogenic, and has anti-carcinogenic properties. The next one is chitosan, which is a linear polysaccharide derived from the chitin found in the shells of shrimp. We chose this one because it also has antioxidant, antimicrobial, and antifungal properties, and we also chose it to modulate the release of lupulon. And the final component we used was gum arabic, which is a natural product obtained from the hardened sap of acacia trees. And it was chosen for its ability to electrostatically stabilize the nanomatrices of our nanoparticles. So these were the steps we took to make the particles. You start by having the ionized water in the beaker under continuous stirring. You slowly drop in first the zane, followed by the lupulon, and then the chitosan in the same way. After letting that stir for 15 minutes, we added the gum arabic solution drop by drop, which would then precipitate out the nanoparticles. Our solutions we then transferred to an ultrasonicator, which would ultrasonicate for 30 minutes to help to dissolve everything. Then our solutions were separated into smaller test tubes that would fit into centrifuge, which we would use to centrifuge for 45 minutes at 10,000 RPM. After they're done centrifuging, you'd separate the liquid from the solid, save the liquid supernatant to run further tests on, and then scrape out the nanoparticles which were at the bottom of the test tube, and then weigh and dry them. Table 1, you could see the mixtures used in their synthesis. You have varying concentrations of zane, lupulin, and chitosan, and all of them have the same amount of gum arabic. And again, this is an anti-solvent procedure where we used propylene glycol instead of flammable ethanol, which is a little bit more dangerous to work in the lab. Table 2, you can see the composition of our nanoparticles after we had already tested everything. You can see encapsulation efficiency is high for lupulin, it's high for chitosan, and it's high for gum arabic. Here I included some nanoparticles that were tested for their size and zeta potential from a previous study that was done. This is just to give you a reference of the size of the nanoparticles. And here I've included some FTIR graphs. This is also just to give you an idea between the differences of the nanoparticles and to show that each of the components are present. The bands on each on our graph, you can see the different components that are present. Same thing on these. Certain bands reveal certain components of our nanoparticles again. And then we assayed them against their activity on MMP1, which is a collagenase. Collagenases break down it causes wrinkles if it's too active, which is why we tested it on our nanoparticles. You can see that some of them were upregulated and some of them downregulated MMP1, which the ones that were upregulating it, you would think that that's something not desirable because it causes wrinkles, but on this occasion, it could be desirable for something like treating wounds so that you don't develop scar tissue. And then obviously downregulating it, as I mentioned before, is good for preventing wrinkles, which means that we could use our nanoparticles for some kind of cosmetic purpose. Here we have antioxidant activity. We measured this by using the Cayman Chemical Antioxidant Assay testing kit, where Trolox was the standard. You should notice here on the side that since lupulin and chitosan were both known antioxidants, we expected our nanoparticles to have these properties. And you'll notice that the particles with chitosan had a slightly better antioxidant property, which is what we were hoping to see. We were hoping to see a synergistic effect between the two of them since they were both known to have these properties. And this is good for displaying their potential in fighting photoaging. This brings us to the effect of chitosan on lupulin release. Another thing we were expecting to see was adding chitosan to our nanoparticles would hopefully increase the release of lupulin from our nanoparticles because of their differing electrostatic attractions. In the first graph, you can see that line in orange is the one that included chitosan, and the gray one too. The blue one didn't have chitosan, and you can see that the release is greater in those that did contain chitosan. Here you'll see the same thing. These were just different concentrations, different ratios of the 3 components. In this figure 7, you'll see in that orange line the immediate jump in the release, which is known as burst release, which is also something you want to see when you're developing nanoparticles like this, that you want to have the components inside be released quickly. And yeah, just to conclude, we used a green method, anti-solvent method with GRASS reagents. All of our components are renewable and biodegradable. And yeah, that's pretty much it. Thank you for listening. And I'm happy to answer any questions in the chat.
Thank you very much, Antonio. Thank you. The next speaker is the undergraduate student from University of Washington, Mayun Jennifer Chun. Will be talking about de novo design of phosphorylation inducible heterodimers. Mayun?
I don't show that she's joined.
Oh, she is not there?
Mm-mm.
What about
And
Raymond?
Raymond's having, he was having his microphone's broken, so he's not going to be able to do his presentation.
Okay. Then probably we need to wind up then.
Mm-hmm.
Okay, then. Thanks very much, everybody, presenters and audiences who sat down throughout the symposium and listened to the presentations. And thank you very much, Daniel, for organizing this particular event. Thank you. Thank you all.
I just wanted to tell everyone that in a few days that this recording will be available on the SCALACS website under event recordings, and I'll send you all a link once it's up there. Thank you, guys.
Thank you all. Bye now.